Greetings, good morning or good afternoon, depending on where you are. We are continuing with our thermodynamic lectures. Today we want to look at the principle of dynamic similarity. This is a principle which is built on the simple premise that if you can know certain characteristics of a smaller unit, and it bears similarity to a bigger unit, then you can extrapolate your data to be able to interpret the behavior of the bigger unit. So in this particular case, where we're talking about principles of dynamic similarity, one of the first things we are going to look at, we want to apply it to forced convection heat transfer in systems. That's why we want to apply this particular principle because remember, most of the equations you have derived, whether it's the Reynolds equation and the rest, it works very well for laminar flow. But when it comes to turbulent systems, we have issues here and there. But in this case of principal dynamic similarity, we are assuming that the physical properties of the fluid do not change with temperature. So we are assuming that the physical properties of the fluid does not change temperature. This is a relatively limited assumption which might not hold over most of the systems, but works pretty well. Now, what are we talking about? First of all, suppose we have a boundary confining some solid body. Let us say that solid body is cylindrical, and of course there is fluid flowing around it. So we consider boundary enclosing a solid body. Let us say this is cylindrical and is fluid flowing around the body. So this fluid flowing in the vicinity of the solid body, we can consider that a field. We can consider that as a field. So the overall space of fluid flowing around the body can be considered as a field. Now, there are certain things which, to bring this concept of similarity, we want to evoke this system, and it should be applicable to both laminar and turbulent flow. So we are saying it should be applicable, should be applicable to both laminar and turbulent flows. Very important to note that. Now, one of the things is that we assume that the solid and the boundary are geometrically similar. So if we have taken two bodies, for example, let's just draw a diagram or a schematic of sorts of the two bodies, schematic of the two representations. Let's do a schematic of the two representations. Let us say we have that there we have a solid. Try to draw it as best as you can. There we have a solid. That's a solid body. Let's say the velocity here is u, a, and the velocity here, ub. And the other one is the same. So again, let's call this ua prime. Let's call this velocity here, this point, ub prime, because this is still solid body. So we are saying that these two representations are we are assuming that the body and the boundary are geometrically similar. So one, A, we assume the solid body solid bodies and the boundaries are geometrically similar. So we are assuming that it's the solid bodies and the boundaries are geometrically similar, because it's the boundary. Two, we are also assuming that the velocity round the boundary, are the same. Finally, we are also assuming that the temperature around the boundaries are the same. So what is the import of this? If A, B, and C are true, then we move on to the next step. If A, B, and C are true, then we can say that then in that particular case, for those two bodies, when the Reynolds numbers are the same in the field, then it implies that their velocities are the same. So when A, B, and C are true, and by the way, for A, B, and C being true, that does not mean does not imply technically that they're dynamically similar. No, that's not sufficient. So we move on a step further. So we are saying the velocities are the same. One, the velocities are the same when the Reynolds numbers in the fields are the same. What was Reynolds number? Remember Reynolds number is the density velocity times length. In the case of the cylinder, we can use the diameter over dynamic viscosity. Always remember that. Dynamic viscosity that will be length, or we can use diameter. There's no problem with that. And that's velocity, and that is density. Secondly, if we can also say that the temperatures will be the same in the fields if the Prandtl number is the same. That is, Reynolds number is the same and Prandtl's number is the same. So we can say the temperatures will be the same when the Prandtl's number are the same. What was Prandtl's number? Remember, Prandtl's number was the dynamic viscosity times the isobaric heat capacity over K, where K is thermoconductivity. Again, mu, we have already defined mu as dynamic viscosity. And it's the same as dynamic viscosity. And so, when the Prandtl's number and Reynolds numbers are the same in both fields, then we can say, in terms of Nusselt number, remember, in terms of Nusselt number, remember Nusselt number? Nu, Nusselt number, in terms of Nusselt number, remember Nusselt number? We had said that Nusselt number, Nu, divided by the Prandtl's number and Reynolds number will give you the Stanton number. Remember, that was the Stanton number. This is Prandtl's number, Reynolds number, Nusselt number. Give you the Stanton number. And so we can get, before we talk about the Nusselt number in terms of the expressions, if the Prandtl and Reynolds numbers are constant, then you know dynamic similarity can be expressed also in terms of Nusselt number, because it's a function. Because remember, Nusselt number is a function of Prandtl's number and Reynolds number. So let's just see what it is based on that. Remember, Stanton number is, so the Nusselt number is Stanton number times Prandtl's number times the Reynolds number. And what was Stanton's number? That was h over rho c pu and velocity. That was Stanton number. Prandtl's number is rho cp, remember, over k, and Reynolds number, remember, was rho u l over dynamic viscosity. So what do we get? The rho will cancel the rho, the velocities will cancel. What else cancels? The dynamic viscosity will cancel, the Cp will cancel. So what do we have? What are we having here? We have h. So Nusselt number will be HL over K. And don't forget, H is the transfer coefficient, L is length, that is the thermal conductivity. Don't forget that. Comes of that. Don't forget these particular quantities. So, If the Reynolds number, as you have specified in terms of those fields are equivalent, then we are talking now of the systems being dynamically similar. Now, this is very important. This dynamic similarity is very important. Why are we saying that? It means that you can have a prototype because, for example, most of the measurements, people prefer to do empirical measurements involving heat transfer coefficient. Determined normally empirically. And so when you can determine some of these things empirically, if you know that they're dynamically similar, then you can extrapolate the values. For example, you can have your prototype, which is a very small unit, but you want to translate it to account for the behavior of a huge unit, for example, a heat exchanger. And once you know the quantities, once you know some of these quantities which are determined empirically, and you know that the systems you are dealing with are dynamically similar, then if you have values like you have mu, you know that you have viscosity, you have specific heat capacity, Cp, you have density rho, you have the thermal conductivity. Then now with all these quantities, which you have gotten experimentally using a smaller unit, if you know that whatever the bigger unit is, you're expecting to be dynamically similar to the smaller unit, then you can actually extrapolate those values knowing those relationships which we have mentioned. So the principle of dynamic similarity is very, very important in extrapolation of system behavior. Let's stop at that point. We'll pick up with other lectures later.